comes to the speed of light, most of us feel familiar. It is not only a physical constant but also one of the core elements, shaping human understanding of the universe and natural laws. Broadly understood, the speed of light is the propagation speed of electromagnetic radiation in a vacuum. It is considered one of the most fundamental and universal constants in physics, involved in theories from quantum mechanics to relativity. However, accurately measuring this value is not easy. Light has existed since the early days of the universe's formation, but understanding and determining its speed is the result of centuries of research, requiring humanity's relentless intelligence and effort. Historically, even eminent scientists of the modern era debated whether light travels instantaneously or at a finite speed. It wasn't until the special theory of relativity emerged in 19 that Albert Einstein laid the foundation for the modern understanding of the speed of light. He not only affirmed that the speed of light is the universe's ultimate limit, but also made it an axiom for fundamental concepts like space and time. Thus, the speed of light is not just a number, but the backbone of modern physics. However, even after determining the value of the speed of light, many questions remain unanswered. Debates surrounding the nature and phenomena related to light continue to challenge the scientific community. One intriguing question is, if in the future, humans build a spacecraft capable of traveling at the speed of light, what would happen to those on board? Would they perceive the contraction of space or the slowing of time, as predicted by relativity? Before the 20th century, Isaac Newton's views on gravity, force, and motion seemed like indisputable truths. But the emergence of Albert Einstein completely changed this worldview. By introducing new theories, he led humanity to a new intellectual landscape, making the speed of light the key to unlocking the deep secrets of the universe. Einstein's theory of relativity resolved many doubts about mass and energy. The mass-energy equivalence equation demonstrated that mass and energy can be converted into each other, meaning mass can be transformed into energy and vice versa. He proposed that there is no standard frame of reference. Everything is relative, even time. From this, it follows that the speed of light is constant and independent of the observer. Therefore, if a person moves at half the speed of light in the same direction as it, the light will appear the same as to a stationary person. The energy-mass equivalence shows that an object's mass can be expressed in terms of its energy. This is illustrated by the famous effect of relativity. If an object moves at 10% of the speed of light, its mass increases by 0.5% compared to its original mass. Similarly, when the speed increases to 90% of the speed of light, the object's mass doubles its original mass. At rest, the total energy of an object, denoted as E, is determined by the product of its rest mass, denoted as m, and the square of the speed of light in a vacuum, denoted as c. This formula is expressed by the famous equation E equals mc squared. If an object is moving relative to an observer, relativistic effects must be taken into account. In that case, rest mass is replaced by relativistic mass, and energy also becomes relativistic energy. Albert Einstein first proposed this formula in 1905 in a paper titled, "Does the inertia of a body depend upon its energy content?" This is one of the famous papers from his miraculous year. So, can we travel at the speed of light? The simple answer is no, we cannot travel at the speed of light. The reason lies in the nature of relativity. As an object approaches the speed of light, approximately 300,000 kilometers, its mass increases exponentially. If it reaches the speed of light, the object's mass would become infinite. This means an infinite amount of energy would be required to sustain its motion, which is completely unfeasible physically. Therefore, no object can reach or exceed the speed of light. This is a fundamental limit of the universe, established by Albert Einstein's special theory of relativity. Setting aside the above factors and posing an example, if you were moving close to the speed of light, what would you see? In the scenario where humans could travel at nearly the speed of light, For example, at 90% of the speed of light, interesting phenomena would occur. First, time would slow down for you. This phenomenon is called time dilation in relativity, causing your time to pass slower compared to a stationary observer. For instance, if you perceive only 10 minutes passing for a stationary observer, the time would have stretched to 20 minutes. In other words, the time you experience is halved. Second, your vision would change significantly. The scenery ahead would transform into a deep tone, and the colors of stars would change due to the Doppler effect. Stars in front would shift to blue as their wavelengths compress, while stars behind would appear red as their wavelengths stretch. At higher velocities, light from the front and back would gradually leave the visible spectrum, leaving everything around you in darkness. Traveling at the speed of light is likely impossible, but if humans could truly experience it, it would certainly be a memorable, once-in-a-lifetime experience. So, is there anything equal to the speed of light? As we know, the speed of light is the maximum velocity limit in the universe. Waves such as radio waves, television waves, radar waves, infrared, and ultraviolet rays can all travel at speeds equivalent to light, as they are also electromagnetic waves. However, to date, no mass-carrying matter has been discovered that can reach the speed of light. Humanity's greatest achievements in approaching this velocity are due to super-powerful particle accelerators, Large Hadron Collider, LHC, or America. These machines can propel subatomic particles to 99.999% of the speed of light. Nevertheless, even these particles cannot achieve the absolute speed of light, as infinite energy would be required to do so. Currently, in the universe, no particle or object has been detected that can equal or exceed the speed of light. The speed of light and the speed of darkness. Some people ask, if there is a speed of light, does something called the speed of darkness exist? In reality, this concept has no physical basis. Darkness is not a substance or energy like light. It is merely the absence of light, a permanent background. However, if considered indirectly, the speed of darkness is essentially the speed of light. For example, in a glass room, when light shines in, the space brightens. When light leaves, everything becomes pitch black. The moment light arrives and depures demonstrates the speed of light, not some independent velocity of darkness. Subscribe to the Guia Nigo channel so you don't miss out on exciting videos.